Welcome everyone. In this video, we will walk across what are sequence to sequence models, and we will see the transformation journey of sequence to sequence models to present day transformers. We will see what are the building blocks of sequence to sequence models, what are their basic subtypes, what were the basic challenges that were faced in sequence to sequence model, and how it led to build up of present day transformers. So to start this journey, let me ask you a question. Imagine asking a computer to translate how are you into French, and you see computer replying command vasto. This is the essence of sequence to sequence learning. It's about mapping one sentence or sequence into another, even when the input and output lengths don't match. Sequence to sequence opened doors for machines translation, where entire set of languages could be bridged together. It powered text summarizations, shrinking long articles into short notes. It gave rise to chatbots that respond naturally and feel like wow, and speech recognition systems that convert audio into text. So in early stages, sequence to sequence model involved recurring neural networks. These were the backbone. The encoder read the input word by word, compressing it into a hidden state. The decoder unfolded the state into the output sequence one token at a time. This encoder decoder design worked well for short sentences. It allowed variable length handling, something earlier models couldn't do. But cracks appeared when, with longer inputs, memory faded, details blurred, and training slowed down because RNNs had to process everything step by step. And with this came the bottleneck of a single vector. The encoder final hidden state became a bottleneck. One vector had to carry the meaning of the entire sentence. Imagine stuffing a whole novel into one page. Details spills out, no sense is lost. The long sentences, this compression destroyed the fine details. Clauses were forgotten, contrasts blurred, and translations lost accuracy. The model had minimal memory, and the burden of a single vector limited the performance. And this is where the breakthrough happened. The attention changed the game. Instead of relying on one compressed state, the decoder could now peek at all encoder states. At each step, it calculated attention weights, deciding which word mattered the most. This created a soft alignment between input and output. The decoder could dynamically focus on the right words at the right time. Suddenly, translations became sharper, summaries more accurate, chatbots more coherent. But even though with attention, RNNs were chained to sequential processing, each step depended on the previous one. GPUs built for parallelism couldn't unleash their full power. The question shifted now from how do I remember this to how can I go faster? Researchers realized that to scale models and datasets, they needed to break free from the sequential dependency. And that is where the revolution started. With attention is all you need. In 2017, Vaswani and the colleagues unveiled the transformer. No recurrence, only attention. Suddenly, models could process all tokens in parallel. Training sped up, models grew larger, datasets expanded. This wasn't just an improvement, it was a revolution. The transformers became the foundation for scaling language models to billions of parameters, unlocking capabilities never seen before. And this is what we see as today age transformers and large language models. Now let's deconstruct the transformer architecture. The transformer has two engines, the encoder and the decoder. The encoder builds a contextual map of the input. Decoder uses that map plus previously generated tokens to produce the output. This modularity gave rise to specialized models. Encoder only designs like BERT for understanding, decoder only designs like GPT for generation, and encoder-decoder hybrids like T5 for translation and summarization. The engine room for this was self-attention. At the heart of the transformer lies self-attention. Each word looks at every other word, weighing their importance. This allows the model to capture relationships across the entire sequence all at once. Self-attention makes language coherent. In sentences, animal didn't cross the street because it was too tired. The word it correctly links to the animal, not the street. That clarity comes from attention. Now let's look into the mechanics of self-attention. Query, which is query, key, and value. Self-attention works like a search system. Each token becomes a query, a key, and a value. Queries ask, keys answer, value provides information. The model compares queries within keys, applies softmax, produces weighted sums of values. This is scaled product attention. It is a mechanism that lets the transformer build contextualized embeddings for every word. But one attention is not enough. How do we see it in parallel? And that is what multi-head attention does. One head alone can't capture everything. Multi-head attention runs several attention mechanisms in parallel. Each head learns different relationships like syntaxes, semantics, long range links, etc. Together they form a richer understanding. One head might track grammar, another meaning, another entities. This combined output gives transformer its depth and versatility. Now let's get into the decoder generating the output sequence piece. The decoder generates the output sequence step by step. It uses masked self-attention to avoid peeking ahead. It uses encoder-decoder attention to consult the input and the feed-forward networks to refine each position to give the output. This balances the generation, ensures fluent, faithful generation. The decoder doesn't just produce words, it produces coherent, context-aware sequences aligned with the input. Now we get into the order and chaos with positional encoding. Attention alone doesn't know order. Positional encoding solves this by adding signals that mark token positions. Using the sine and cosine functions, the model learns both absolute and relative positions. This gives attention a sense of sequence. Without positional encoding, dog bites man and man bites dog would look the same. Encoding preserves meaning by preserving the order. Thus, a new foundation of transformer family is built. Transformers modularity with encoder and decoder gave birth to a family of 3 types of models: BERT for understanding, GPT for generation, T5 for translation. Each variant adapts the same building blocks to different tasks. This flexibility made transformers the foundation of modern AI. They became the universal architecture for language, vision, biology, audio, code generation, and a lot of other tasks. If we look into the journey of how this transformer era evolved, it started way back, but from 2017 onward, transformer reshaped AI. BERT revolutionized understanding in 2018, GPT-2 amazed with fluent generation in 2019, GPT-3 scaled to unprecedented levels in 2020. Transformers became universal building block, powering breakthroughs across domains. They didn't just change language models, they changed AI itself. So the final takeaway, we have journeyed from bottlenecks of RNN to the revolution of transformers. We saw how attention solved memory problems, how parallelization solved speed limits, and how modularity gave rise to BERT, GPT, and T5. The takeaway is clear: transformers aren't just model, they are foundation for learners and creators, and the step forward are to learn about these. This course will help you to get the basics of as to what transformers are, and you can get on with different tools like ChatGPT, like Microsoft Copilot, Google Gemini, and a lot of other vendors to see these transformers into action and get the most of it out of them. Thank you. If you like this video, please leave your comment, subscribe. Thank you.